Hello, this is Bob from Test Equipment Chronicles with Bob. And today we're going to take a close look at one of the most important fundamentals in automotive electrical diagnosis. Understanding the difference between analog and digital meters, and why that difference matters in the real world. This lesson is built around four main ideas: analog versus digital meter behavior, impedance and loading effect, correct meter application, and voltage drop diagnostic strategy. Now, this is not just about identifying what kind of meter you have in your hand. It goes quite a bit beyond that. The real goal is to understand how the meter behaves in the circuit, how it can help the technician, and in some cases how it can actually influence the reading if the wrong meter is used in the wrong place. So as we move through this presentation, think of the meter not just as a measuring device, but as an analyzer. Because really, the better you understand a tool, the better you understand the circuit. Slide 2. Why this matters. The first question is simple. Why does this matter? Well, it matters because meter choice affects diagnostic accuracy. If the technician chooses the wrong instrument, or even uses the right instrument in the wrong way, the reading can be misleading, and that can send the diagnosis off in the wrong direction pretty quickly. Analog and digital meters do not behave the same. They may both measure voltage, current, and resistance, but they do not always interact with the circuit in the same manner. And that difference becomes very important in modern automotive systems, especially where electronics and low current signal circuits are involved. Wrong meter connection is another major issue. A voltmeter, an ammeter, and an ohmmeter each have to be connected differently. If the student does not understand that, he may get a false reading, or worse, damage the meter or the circuit. So the larger goal here is to move from simple meter familiarity over to real diagnostic understanding. We are not just learning how to read numbers, we are learning how to use the meter to make better decisions. And that is kind of the whole point. Slide 3. Analog versus digital overview. Let's start with the broad comparison. An analog meter uses a needle and a calibrated scale. That means the technician has to interpret what the needle position means. In many cases, he also has to account for the selected range and read the correct scale. So analog meters require visual interpretation and, at times, a little bit of mental math. There is some real historical value in that. Analog meters could be very useful for seeing trends, sweeps, and movement. A fluctuating signal could sometimes be easier to recognize by watching a moving needle than by reading changing digits, and that was one of their strengths. Now compare that to a digital meter. A digital meter gives you a direct numeric display. That makes it easier to read, easier to teach, and easier for most students to trust. Many digital meters are also auto-ranging, which further reduces the chance of setup error. So from a training standpoint, digital meters are easier to bring students into. From a diagnostic standpoint, they are also better suited to modern automotive work. That does not make analog meters unimportant historically, but it does explain why digital meters became the standard and, stayed there. Slide 4, units. Students must read correctly before a student can become good with a meter. He has to become comfortable with the language of measurement. That starts with the prefixes. M means mega, and that means 1 million. K means kilo, and that means 1,000. Lowercase m means milli, and that means 1,000th. And lowercase u represents micro, and that means 1 millionth. Now this sounds basic, But this is one of those areas where students can make real mistakes. If a student confuses millivolts with volts or kilo ohms with ohms, the number on the display may be correct, but the interpretation will be wrong. A voltage drop of 0.2 of a volt is 200 millivolts. Now, that is not the same as 20 millivolts. 1 kilo ohm is 1,000 ohms. 1 mega ohm is 1 million ohms. Those are major differences, and the diagnostic conclusion changes with them. So one of the first things a technician has to do is slow down, read the unit correctly, and make sure the number is being understood in the right scale. Because if that part is wrong, everything after that gets shaky. Slide 5, voltmeter fundamentals. Now let's talk about the voltmeter. A voltmeter measures voltage, and just as importantly, it measures voltage drop. A lot of students first think of a voltmeter as something used to check battery voltage. And yes, that is true. But it is only part of the story. In actual diagnosis, voltage drop testing often becomes one of the most useful functions the meter has. A voltmeter is connected in parallel. That means it is placed across the part of the circuit we want to evaluate. Across the battery, across a bulb, across a switch, across a connection, across a cable, or across a ground path. That rule matters. A voltmeter connected in series is not being used correctly, and the reading will not mean what the technician thinks it means. Lead placement also matters. The reading only has value when the technician understands exactly what 2 points are being compared. So at this stage, the student has to move beyond just turning the meter on. He has to start thinking in terms of circuit position and test purpose. That is where meter use starts becoming real analysis, not just meter handling. Slide 6, meter loading effect. Now we get into one of the most important ideas in the whole presentation, and that is loading effect. When you connect a voltmeter to a circuit, the meter is not just passively watching. It actually becomes part of the circuit. That means the meter itself can influence the circuit being measured. If the meter resistance is too low relative to the circuit resistance, the meter can load the circuit down. In other words, it changes the circuit enough to distort the reading. And when that happens, the technician is no longer seeing the untouched circuit value. He is seeing a value affected by the meter. That is loading effect. This matters most in higher resistance circuits and in electronic systems where small changes in current flow can alter circuit behavior. A low impedance meter can become a problem in those situations. One of the major reasons digital meters are preferred is that they reduce this problem. Their higher impedance means they have less effect on the circuit. So the reading is more likely to represent what the circuit is really doing. That is not just convenience. That is diagnostic accuracy. And that is a very big deal. Slide 7, impedance, the big difference. Now let's define the term that drives that behavior. Impedance, Al, in this discussion, is the meter's internal resistance. It is the resistance the meter presents to the circuit when it is connected. Analog meters are rated in ohms per volt. That means their internal resistance changes depending on the scale being used. So the same analog meter can behave differently depending on how the technician sets it up. That is one reason analog meters demanded a stronger understanding of the instrument itself. The user had to think not only about what he was measuring, but also about how the meter range affected the meter's own resistance. Digital meters are different. Most digital meters used in automotive work have a fixed input impedance, often around 10 mega ohms or higher. That higher impedance means the meter draws very little current from the circuit, so it disturbs the circuit much less. So when we say higher impedance means less loading, what we really mean is this. The digital meter is more likely to tell the truth without changing the circuit very much in the process. And that really is one of the biggest reasons digital meters won out. Slide 8, example, why a digital meter wins now. Let's put some numbers to that concept. Suppose we have an analog meter rated at 20,000 ohms per volt, and we are using it on the 20 volt scale. That gives us an effective meter resistance of 400,000 ohms. Now imagine we are measuring across a 1 million ohm portion of a circuit. In that situation, the analog meter is now a significant part of the circuit. It loads the circuit enough to change the reading. Now compare that to a digital meter with an input impedance of 10 mega ohms. That digital meter has much less effect on the same circuit. The circuit stays much closer to its natural operating state, and the reading is much closer to the real value. So the digital meter wins because it interferes less. That matters a lot in modern automotive systems. Once you start dealing with control modules, sensor circuits, reference voltages, and other low current electronics, a meter that disturbs the circuit can easily send a technician the wrong way. So this was not just a convenience shift from analog to digital. It was a real improvement in diagnostic quality, and in a lot of ways, that is the lesson. Slide 9, amp meters. Now let's move into current measurement. An amp meter measures current flow. Voltage tells us electrical pressure. Current tells us actual flow through the circuit. Those are not the same thing, and both matter. An amp meter must be connected in series. That is a hard rule. The current has to pass through the meter for the meter to measure it. That means an amp meter is inserted into the circuit path. It is not laid across the circuit the way a voltmeter is, and this is where students can get into trouble. If an amp meter is connected in parallel, especially across a power source, the meter's low internal resistance can create a serious fault condition that can damage the meter, damage the circuit, or create a dangerous situation. So one of the most important memory rules in electrical diagnosis is this: voltmeter in parallel, ammeter in series. If the student locks that in early, he avoids a whole lot of mistakes later. And honestly, some expensive ones too. Slide 10. Ohm meters. Now let's talk about the ohm meter. An ohmmeter is self-powered. That means it uses its own internal battery to apply a test signal through the component or circuit being measured. Because of that, an ohm meter must never be connected to a powered circuit. That is another hard rule. If outside voltage is present, the reading will be wrong. And depending on the situation, the meter or the circuit can be damaged. Analog ohmmeters also required zeroing. Before using them, the technician often had to short the leads together and adjust the meter so it read correctly. So again, analog meters required more user setup and more discipline. Digital meters are generally safer for solid-state circuits. But that does not mean ohm testing is always the best diagnostic method. A component or cable may pass an ohm check with the tiny current provided by the meter and still fail badly when the circuit is actually loaded. That is where many students need the next step in their thinking, because the low current test is not always telling the whole story. Slide 11. Bridge to diagnosis. This is the turning point in the lesson. Many students know how to operate the meter, but they still miss the diagnosis. They know how to select volts, ohms, or amps. They know where the leads go in a general sense, but they do not yet understand how to use the reading to tell the story of the circuit. That is why the meter has to become more than a display. It has to become an analyzer. And the bridge from simple reading to real reasoning is voltage drop testing. This is where the technician stops asking only, what number do I have? And starts asking, what does this number mean under real circuit load? That question changes everything. Circuits can look fine when unloaded. A weak cable, a corroded terminal, or a bad ground may show very little problem with almost no current flowing. But put the circuit under operating load, and now the weakness shows itself. That is why voltage drop testing is so powerful. It makes hidden resistance visible. And that, in my opinion, is where electrical diagnosis starts getting really interesting. Slide 12, starter circuit example. Now let's apply that to a high current automotive example. The starter circuit. Starter circuits can hide high resistance very effectively if the wrong test method is used. An ohm check on a starter cable may look acceptable because the ohmmeter applies only a very small test current. Under that tiny current, the cable may appear fine. But that is not how the starter uses the cable. When the starter engages, current demand rises sharply. Now the cable has to deliver real current under real load. If there is resistance in the cable, in the terminal, or in a connection, the voltage drop becomes visible immediately. That is why a voltage drop test during crank reveals the truth. The circuit is operating, the parts are under stress, and the reading now reflects the real condition of the circuit. By checking the feed side and the ground side separately, the technician can pinpoint where the voltage is being lost. That is no longer guessing. That is a directed diagnosis based on circuit behavior. And that is exactly the skill we want students to develop, because that is real shop level thinking. Slide 13, high resistance circuit example. Now let's move to the opposite type of circuit, high resistance and electronically sensitive circuits. In these circuits, meter choice becomes extremely important. A low impedance analog meter can distort the reading simply because it affects the circuit too much when connected. That makes the meter itself part of the problem. A high impedance digital meter is usually the better choice because it has much less effect on the circuit. It allows the technician to measure the signal or reference value without dragging the circuit down. This becomes especially important in modern automotive work with sensors, control modules, and low current signal path. In those systems, even a small distortion in the measurement can change the conclusion. So one of the more mature habits a technician can develop is this. Before testing, think about the type of circuit, ask what the circuit does, what kind of resistance it likely has, and what kind of meter behavior is appropriate. That kind of thinking separates casual testing from real diagnosis, and you know, that is what we're after. Slide 14, design criteria for teaching. This topic now, from a teaching standpoint, there are some very strong design rules here. First, keep one major concept per slide. Students do better when each slide has a clear focus and does not try to do too much at once. Second, side-by-side analog versus digital comparisons work well because they help students organize the differences visually. One tool behaves this way, the other behaves that way. Third, show lead placement clearly. A lot of confusion disappears when the student can actually see how the meter connects to the circuit. Fourth, separate meter function, meter connection, and diagnostic meaning. In other words, what does the meter do? How is it connected? And what does the reading mean? Those are three separate teaching layers, and they should stay clear. And finally, use real automotive examples, starter circuits, sensor circuits, ground paths, and switch circuits make the topic practical. That is how the information becomes useful instead of just academic. And that is really important in a technical program. Slide 15. Knowledge check. Now let's review the key points. Why is a digital meter easier to read? Because it provides a direct numeric display and reduces interpretation error. What is the loading effect? It is the condition where the meter changes the circuit enough to alter the reading. Why does impedance matter? Because the meter's internal resistance affects how much influence the meter has on the circuit being measured. Why must voltmeters be connected in parallel? Because they measure the potential difference across a component or a section of the circuit. And why is voltage drop testing better than ohm testing on starter cables? Because the starter circuit is a high current circuit, and voltage drop testing under load reveals real resistance losses that a low current ohm test may completely miss. If a student understands those 5 ideas, then he has the foundation needed to move into stronger electrical diagnosis. And that is a very solid start. Slide 16, continue your electrical training. Thanks for watching Test Equipment Chronicles with Bob. If you got value from this lesson, subscribe to the channel, return for the next training segment, and continue building stronger diagnostic skills one step at a time. There is a lot more to cover in automotive electrical training, and the more you understand the meter, the better you will understand the circuit. Stay with the channel, keep learning, and we'll see you in the next lesson.